Hi, everyone. Thanks for coming. How's everyone doing? Good. Almost full day in, 2.5 roughly to go. Cool. So we'll talk about data quality today. I originally planned just to present slides, but a few people came and said that they want to see demo. So demo's cool. Want to see demo? Great. Cool. So who is using Databricks? Great. Who is migrating to Databricks? Wow, lots of people. Very cool. So hopefully this will be useful. All right, so super quick intro. My name is Gleb. I am CEO and co-founder of Datafold. We are a proactive data quality platform, so we help automate testing for data engineers building on Databricks and modern data stack in general. Previously, before Datafold, I was a data engineer for my entire career, and I had a pleasure of building 3 different data platforms, including Autodesk and Lyft. And the reason why I am talking to you today is because I was lucky or unlucky to bring down entire data platform of Lyft with a 2 SQL line code change. And the way it happened is I was an on-call engineer, and I was woken up by an alarm at about 2:30 a.m. because one of our pipelines in Airflow got stalled. Some bad data entered our event stream, so I had to filter this out. So I figured out a SQL query that would actually do that. I introduced the change, got a +1 from another poor data engineer woken up the same time with me, merged it, everything looked green, and the next day I come to work and you kind of see where it's going, right? It's not going to end well. The craziest thing wasn't that my change corrupted one of the primary data sets, actually the data set that was describing rides, the core concept for Lyft. The craziest thing here was that it took us 6 hours in the war room, with me being present in the war room, to be able to correlate all the weirdness we were seeing in the dashboards and our feature sets and machine learning models to the change that I made just a few hours back. So to me, this was a major realization that, well, 1, it's very easy to screw up our data pipelines. 2, I should learn SQL. And 3, that once something is broken, it's usually, well, it can cause massive impact, especially at a company like Lyft, which is incredibly data-driven. And it's too late when you find about issues in production. So that kind of set me on a journey of building data tools, and luckily I wasn't fired from Lyft. I was actually, I became a product manager building testing tools, and here I am today talking about data quality and testing. So in general, this is not unique to me. I think many of us in this room have been in similar situations, hopefully with less negative impact than I had. But in general, this type of problem bugs us, right, in our workflow as data engineers. So data quality issues go unnoticed, or we detect them too late. We can't find the root cause of the problem, and we engage in a lot of firefighting and not enough building, right? So there's no Gen AI is happening until our data pipelines are in good shape. And what's exciting is that software engineers, they figured out this solution to similar problems a few decades ago, and they call it shift-left quality, or shift-left QA, shift-left testing. So who knows what shift-left means? What does it mean? Correct. So that, yes, basically you're shifting it to the left in your data stream or in your developer workflow. So thank you. So basically, I think there are 2 dimensions to talk about here. 1 is your typical developer process, right? So typically the way we work as data engineers is we write some code, we propose our changes, we deploy them, and then we monitor what happens with our stakeholders and dashboards in production. So the worst state, and the state I found myself with this 2 SQL line code change, is that your data breaks in production and you actually learn from your users that something is wrong. This is a very bad place, right? So it couldn't get worse than that. Now, something better is that data breaks in production, and we have some sort of monitoring, some sort of checks that are alerting us to this problem. That's a better state, but still, it's in production. Likely some damage is already done. We have to firefight. we have to drop whatever we're doing and go and remediate this issue, so not ideal. So something we can do better is potentially detect these issues before they get to production. So in the context of the developer workflow, that means before we merge our code and deploy our code, for example, SQL running on Databricks to production. And ideally, we actually do this even before we stage our changes, so we find out about issues in our IDE. So as a software engineer, you can enjoy co-pilots and a lot of static analysis support in IDEs. Data engineers are not there, so if you can move it at least from production to staging, that's already a good state. And it is hard. It is hard to shift left. Why it's hard? Because we're dealing with a lot of code, a lot of business logic that runs on very complex, constantly changing data. When we are changing code, which happens a lot because we have to ship new products, we have to keep up with business demands, the big question is, how do we test a change like that, right? So simple modification to SQL, but how do we make sure that there are no regressions introduced or no unwanted changes, no metric drift? It's hard. And there are multiple solutions to that. We can run assertion tests like Great Expectations or ZBT tests. We can write unit tests. We can run some queries to check our changes. We can ask our colleagues to review our code. But all of these solutions are important. We have to do all of them. But what all of them have in common? They're not scalable. Because in a world where you have thousands of source tables and you have thousands of derived tables and you have a lot of downstream use cases for our data. Again, back at Lyft, we had about 13,000 data science reports, 13,000 that were circulating and people were using. So it's just impossible to cover every single potential failure, every single column with those tests. So what do you do? And the answer to that lies in the answer to this very simple question. When we're making changes to our code, how do we know exactly what kind of impact a code change makes on our data? On the data we change, on everything downstream, on our business applications. So, and now I'm going to show you a demo. So bear with me. Hopefully it all works out. Cool. So this is, now we're talking about the solutions. So this is a typical pull request. And here we have one model that runs on Databricks modified. It's a DMorgs table, so it's a table that describes organizations in our CRM. And we introduce a case when statement that basically remaps the plan that organization is on, as well as introduces the logic for how we calculate the number of users for the organization. So very simple PR. So to answer the question, how does the code change impact the data, we run what's called a data diff. A data diff is essentially a Git diff, but for actual data, and it helps us answer the question, how does the data change between our dev branch of the code and main branch of the code? To answer this question, we compare data in production with our staging environment. And here, right in the pull request, we can see that, OK, this table is modified. We're actually going to have fewer rows as a result of this change. We're going to have 2 columns that will change based on this modification to the logic. Now, this is a fairly simplistic report. And if we want to investigate it in a greater detail, we can go to Datafold, which is the app that we're building. And we can look at this diff at a greater detail if Wi-Fi permits me to load this. Bear with me. Cool. OK, so now we have this more detailed diff report. And we can actually look at this almost as a Git diff view, right? So here, what we look at is, for every primary key in this table, what is the change between the main branch of the code, so data produced by the main branch, and the data produced by the testing branch. And we can see that we indeed remapped some of the values from team to individual. This remains the same. Now, are you going to QA your billion row table with this? Probably not, but it's still a very helpful sample of your data that gives you an idea of the nature of the change. We can also look at this change in a more aggregate way, right? So here for every column, we compare the distributions, and we can see, for example, that the subplan column where we changed the case one statement went from having 2 values, business and team, to having 3 values. So imagine that this is not, a simple column, but it's a feature that you use in a machine learning model. So now you know exactly how the distribution of your feature is changing. You can also see what rows have been introduced or taken out of the table by the change. But what's also important is changes we make to the code, they don't exist in a vacuum, because in a large organization, you have other people building things on top of the data that you produce. So what's really important is understand the downstream impact. So to understand downstream impact, we have column-level lineage engine that essentially looks at all the SQL that was ever executed in your warehouse, builds the lineage graph, and then builds this all the way to your BI tools. So you can actually see in a graph representation, how does this code change propagate throughout your entire DAG. So in this case, for example, we know that we changed the subplan column, and we can see all the downstream tables as well as Tableau dashboards in this case that are going to be affected because they pull this data into data sources, workbooks, and dashboards. So now with this simple analysis, we went from pretty much vague idea of what this code change is doing to having pretty good understanding of how did the data change all the way to downstream applications. In terms of how this is implemented, it depends on what kind of data orchestration you use. So for example, if you use something like Airflow or Azure Data Factory, or you just maybe have a Git repo with your Databricks notebooks, you can run the same process by essentially telling Datafold what to compare. If you use something like dbt, this process is fully automated. So we pick up changes that were introduced by code change, and then we rely on dbt manifest to build a staging environment and compare it. Cool. So the CI part that I demonstrated is actually really important because if you run it in CI, you go from ad hoc testing, so kind of best case, we hope your engineer tested it, to having guardrails for every team member to see what's going to happen to their data, which also helps code reviewers, right? So a big challenge that I ran into in my career as a data engineer is that core data engineering team has a lot of context about their data, right? So they can develop and they know exactly what everything means. They can move fast and with high confidence, even with minimal testing. But if you're trying to democratize your data, so you have maybe less technical folks like analysts, people from finance, or someone who's not doing data engineering every day 24/7, contribute. So that really helps because you know that whatever they do with the code, you have full idea of how that is going to impact it. So something I'm really proud of is our work with Moody's. So Moody's is a financial data company, and they are very advanced in their not only data engineering, but also building AI products on top of the data that they produce. They have over 1,500 dbt models running in production, and they have a very, very extensive test suite, assertion test suite, and we help them ensure that for any change that they make, we help catch whatever unexpected issues may be occurring. So Ryan is doing much better than I did at Lyft, building those pipelines. Cool. So we talked about shifting left within the context of a developer process. But can we apply the same concept to production? So what does that mean? If we consider a typical flow of data, right? So we have source data represented usually by events, replicas of our production systems, as well as exports from APIs like Salesforce. We get this data into our data warehouse or data lake. We then transform it using data orchestrators, and then we push it to BI apps, reverse ETL, ML apps, right? Very kind of simplistic view, but roughly generalizable. Shifting left means that data flows left to right. That means we want to apply data quality focus as close to the source data as possible. Because if you have really good control of quality of the code that runs in the data warehouse with CI and automated testing, then things that can break are really related to unexpected things happening with your source data, right? Because all the transformations are already taken care of. So A good example is of shifting left is making sure that when you sync data from your transactional sources to the data warehouse, the data lake, the data stays in sync, right? So we replicate data from transactional stores into data lakes. That is done a lot of times using CDC or change data capture, and that is quite a complicated process. A lot of things that can go wrong. There are a lot of trade-offs. Every system that runs CDC at scale has, like, do you want exactly one's data or no duplicates? And if you don't have your source data correctly landing in the data lakehouse, then it's sort of a no starter for anything downstream, because a lot of times OLTP extracts are considered our source of truth because, well, events are even less reliable. So what can we do in terms of shifting data quality to the left to ensure that our source data lands correctly? Data diff, again. But in this context, data diff helps you compare data between source and target, right? So in the context of developer process, we talked about staging versus production. And here we're comparing production and production, where source is, for example, your Postgres instance, and target is your lakehouse. And what's cool about this is you can see the discrepancies at the value level, and that helps you remediate any kind of issues happening in production. So source to target, reconciliation, a great way to ensure that your source data is correct. Now, you may have some questions. So how does it work? Does it mean that we need to import all the data from both places and compare it somewhere? How fast is it? So quickly, it works using stochastic checksumming. What that means is we are pushing the compute in place to both source and target. We're not extracting data to compare it. And that allows us to do the consistency checks both fast and with great detail. And it could be very fast. It really is bottlenecked by the speed of underlying engine. If this is something like Snowflake to Databricks, it could process billions of rows in minutes. If this is something like transactional store like SQL Server, could be slower just because those are not columnar-oriented databases. But in general, you can achieve very good precision to speed trade-offs. And if your data is really big, or if you have a database very sensitive to load, you can always use sampling. And you can run this monitor consistently so that you can be notified whenever data is not consistent. Cool, so a few of you told me that you're running data migrations. So the same concept can be applied to migrations. Why talk about migrations? Migrations are hard. I spent 3 years of my life migrating Lyft's data platform from Redshift to a data lake, and I also failed because of how hard it was to reconcile the new world with the old world. And if you don't reconcile it, if you don't prove to your business that whatever you do on the new technology is fully replacing, is fully matching whatever people were using for years on the old system, business is not going to adopt the new system. Your project gets derailed, budgets are exploding, and it's a misery as a data engineer to work on such a project. So migrations can be between data platforms, or they can be between data transformation frameworks. And a really important aspect of the migration is to make sure that you have full validation that your new data matches legacy. If you do that, then a lot of other aspects of the migration project are simplified. And data diff comes to the rescue again. In this case, you can use it to compare data again between your legacy source and your new target. You can use it for refactoring, so you can use it as you move your, let's say, legacy transformation logic into more modern tools like Dexter and dbt, and you have full visibility into the discrepancies. And you can even share these reports with your stakeholders, make sure that they sign off and your project moves fast. Again, my personal failure, I got to turn around and work with amazing customers. So we did help a number of organizations, including data teams at Eventbrite and FAIR, accelerate their migrations projects. FAIR was really big, so 5,000 plus tables migrated. And we helped them accelerate migration by over 6 months because they had automated testing. They also did a cool thing where they actually scheduled the entire data platform, the legacy platform, and the new platform to be diffed for every table every day, so that every day they knew exactly how far apart those systems were, and they could basically quantify the percentage of the migration project done, which was really cool. Great, so shifting to the left. Again, as a quick recap, you can do it in the developer context. When you're making changes to transformations, you do it in production by applying data quality at the source. And you can do it in migrations, because if you are just starting to build on a new platform, you want to make sure that whatever data is there is already correct. So happy testing and happy diffing. And all of this is basically to get ahead of any data quality incidents and shift from being reactive to proactive and preventing them.